Have you ever noticed how some places on Earth feel shaped by forces so extreme they seem unreal? In this episode of Unearthed Secrets, we explore burning lakes, explosive volcanoes, shattered landscapes, and deserts turned to glass. Like and subscribe, and tell us where you're watching from and what time it is for you right now. The lake that turns life to stone. In northern Tanzania, near the border with Kenya, there's a lake whose surface often glows red, pink, or orange under the sun. Along its edges, animals appear frozen in lifelike poses, wings spread, necks curved, bodies rigid as if caught mid-movement. The water looks calm, shallow, and deceptively serene. Yet this is one of the most chemically extreme lakes on Earth. This is Lake Natron, a place where water burns like alkali, where survival demands exact adaptation, and where life and death exist in a delicate, unsettling balance. The Lake Natron lies within the East African Rift Valley, a vast tectonic system where the African continent is slowly pulling itself apart. The lake sits at the foot of Oldonyo Lengai, an active volcano whose eruptions feed the basin with minerals unlike those found anywhere else on Earth. Together, rifting, volcanism, heat, and evaporation have created a lake that defies nearly every expectation of fresh water. Life. Lake Natron is shallow, often less than 3 meters deep, and its size fluctuates dramatically with the seasons. During dry periods, much of the lake evaporates, leaving behind wide salt flats and polygonal crusts that crack underfoot. During wetter months, rainfall and inflow briefly expand its surface, but regardless of size, its chemistry remains extreme. The lake's defining feature is alkalinity. Water entering Lake Natron carries dissolved sodium carbonate and other alkaline minerals weathered from volcanic rock. As intense equatorial sun evaporates water faster than it can be replenished, these minerals concentrate. The result is water with a pH that can exceed 10.5, comparable to household ammonia. At the same time, water temperatures can rise above 40 degrees Celsius in shallow areas. This combination, high alkalinity and high temperature, creates conditions lethal to most organisms. Skin can burn, eyes can be damaged. Many animals that stumble into the lake do not survive. The red coloration of Lake Natron comes from biology, not reflection. Specialized microorganisms, particularly haloarchaea and cyanobacteria, thrive in the alkaline water. These microbes produce pigments, including carotenoids, that protect them from intense sunlight. As their populations bloom, the lake turns shades of red and orange, sometimes streaked with white salt deposits. These same cyanobacteria form the base of the lake's unusual food web. Despite its hostility, Lake Natron is one of the most important breeding sites in the world for lesser flamingos. These birds feed almost exclusively on the cyanobacteria that flourish here. Their specialized beaks filter microscopic organisms from the water, allowing them to exploit a resource unavailable to most other animals. For flamingos, Lake Natron is not a death trap. It is a refuge. The lake's caustic conditions deter predators. Few mammals, reptiles, or birds can tolerate prolonged exposure. As a result, flamingos nest on isolated salt islands and mud flats, relatively safe from disturbance. Millions of birds may gather here during peak breeding seasons, turning the landscape into a moving field of pale pink. The breeding process is tightly linked to the lake's fluctuating levels. When water recedes, salt crust and mud platforms form, ideal nesting grounds. When water rises, these areas become isolated islands, further protecting nests. Flamingo chicks hatch into an environment that would kill most animals. Their legs and skin are adapted to withstand alkaline water. Over time, their diet of cyanobacteria gives them their characteristic pink coloration, yet even flamingos walk a narrow line. If water levels rise too much, nests flood. If drought becomes too severe, food supplies decline. Climate variability directly affects breeding success. Lake Natron's balance is fragile. The lake's reputation for turning animals to stone comes from real observations, though often misunderstood. Birds and bats that die near the lake may become coated in mineral deposits as alkaline water dries on their bodies. Over time, salt crystallizes on feathers and skin, preserving the corpse in rigid, lifelike positions. These remains are not true petrification. No mineral replacement occurs, but the effect is striking. Bodies appear mummified, frozen in time by chemistry rather than geology. Photographs of these remains have circulated widely, contributing to Lake Natron's ominous reputation. But death here is not universal. It is selective. Most animals avoid the lake naturally. Those that perish often do so by accident: disoriented birds, exhausted migrants, or animals weakened by other causes. The lake does not hunt. It simply does not forgive mistakes. Geologically, Lake Natron owes its existence to tectonic motion. The East African rift is slowly splitting the continent into two plates. As the crust thins and fractures, magma rises, volcanoes form, and basins subside. Lake Natron occupies one of these basins, collecting runoff from surrounding highlands and volcanic slopes. Old Doinyo Lengai, the Mountain of God in the Maasai language, plays a crucial role. It is the only active volcano on Earth known to erupt natural carbonatite lava, a rare type of lava rich in sodium and potassium carbonates. Unlike typical lava, it flows at relatively low temperatures and appears dark or even black when fresh. As this lava weathers, it releases sodium carbonate into the environment, directly feeding Lake Natron's chemistry. This unique volcanic input is one reason the lake's alkalinity is so extreme. The surrounding landscape reflects this harshness. Vegetation is sparse near the lake's edge, giving way to grasslands and acacia scrub farther away. Heat shimmers across the flats. The air often smells faintly of minerals and sulfur. Despite the environment, humans have lived around Lake Natron for centuries. The Maasai people inhabit the surrounding region, herding cattle and goats across the savanna. They understand the lake's dangers and benefits intimately. Livestock are kept away from the most alkaline areas. Seasonal movement avoids the worst conditions. The lake is respected rather than feared. To the Maasai, Old Doinyo Lengai is sacred, and the landscape around Lake Natron is woven into spiritual belief and daily survival. The lake's extremes are part of the land's identity. Scientifically, Lake Natron is invaluable. It serves as a natural laboratory for studying extremophiles, organisms that thrive in conditions once thought uninhabitable. The microbes here offer insight into early Earth conditions, when oceans were more alkaline and life was just emerging. Astrobiologists study similar environments to understand how life might exist on other planets or moons, such as Mars or Europa. If life can persist in Lake Natron's chemistry, it expands the definition of habitability. The lake also illustrates how ecosystems can be built on narrow tolerances. Remove or alter one factor, alkalinity, temperature, inflow, and the entire system shifts. In recent years, Lake Natron has faced increasing pressure. Proposals for soda ash extraction raised alarms among conservationists, who warned that altering water inflow or chemistry could devastate flamingo populations. Infrastructure development, water diversion, and climate change pose additional risks. Flamingos depend on a small number of alkaline lakes across East Africa. Disrupt one, and the impact ripples across the entire species' breeding network. Climate change adds uncertainty. Altered rainfall patterns could dilute or concentrate the lake's chemistry. Increased evaporation could intensify conditions beyond tolerable limits. Changes upstream could reduce inflow entirely. For now, Lake Natron remains extreme but stable. Hostile yet life-sustaining for those adapted to it. Visually, the lake is constantly changing. From the air, it looks like a painter's palette. Reds, whites, pinks, and browns, shifting with water levels and microbial blooms. From the ground, it feels vast and exposed. Heat presses down. Sound carries far. The horizon blurs. At sunrise and sunset, colors intensify. Flamingos move in shimmering groups, their calls echoing across the flats. Salt crystals catch the light. Steam may rise from warm shallows. At night, temperatures drop sharply. The lake darkens. Stars reflect faintly off wet salt. Silence returns. Lake Natron challenges the idea that beauty and danger are opposites. Here they coexist. The same chemistry that burns skin feeds birds. The same isolation that kills intruders protects newborn chicks. It is not a lake of death. It is a lake of specialization. Only those precisely adapted can remain. In this sense, Lake Natron is a reminder that nature does not aim for comfort or fairness. It creates conditions, and life either adapts or disappears. Where adaptation succeeds, ecosystems flourish, even in places that seem impossible. The red waters do not signal warning. They signal balance, one achieved on terms entirely unlike our own. In northern Tanzania, beneath a relentless sun and beside a restless volcano, Lake Natron continues to glow, evaporate, reform, and endure. A lake that burns, a lake that feeds, a lake that shows how narrow the line between life and stone can truly be. The volcano seen from space, on a remote island in the Northwest Pacific Ocean, far from cities, shipping lanes, and permanent settlements, a volcano rises steeply from the sea. Its slopes are dark, bare, and sharply defined. There are no forests softening its outline, no towns clustered at its base. When it erupts, there is nowhere for the force to go but upward. Ash punches through clouds. Shockwaves ripple across the atmosphere. From orbit, the eruption looks almost unreal, a perfect white ring, expanding outward from a dark cone at the center. This is Sarachev Peak, one of the most explosive and visually dramatic volcanoes on Earth. The Sarachev Peak is located on Matua Island, part of the Coral Islands chain that stretches between Russia's Kamchatka Peninsula and Japan's Hokkaido Island. The corals sit directly along the Pacific Ring of Fire, where tectonic plates collide, descend, and melt, feeding some of the planet's most active volcanoes. Sarachev Peak is among the most powerful of them, not because it erupts constantly, but because when it does erupt, it does so with extraordinary force. Sarachev Peak rises to about 1,146 meters above sea level. It dominates Matua Island completely. The island itself is only about 52 square kilometers in area, meaning the volcano defines nearly every aspect of the landscape. From any vantage point, Sarachev Peak is unavoidable, a single cone rising from ocean to summit without interruption. Unlike volcanoes surrounded by valleys, cities, or forests, Sarachev stands exposed. This isolation is part of what makes its eruption so striking. To understand why Sarachev Peak behaves the way it does, it is necessary to understand the tectonic setting beneath it. Here, the Pacific Plate is being forced beneath the Okhotsk Plate, a fragment of the larger North American plate, in a process called subduction. As the Pacific Plate descends, it heats and releases water into the overlying mantle. This lowers the melting point of rock, generating magma. That magma rises through fractures in the crust, feeding a chain of volcanoes that includes Sarachev Peak. This process has been active for millions of years, building the Coral Island arc one volcano at a time. Sarachev Peak is a stratovolcano constructed from layers of lava, ash, and volcanic debris laid down by repeated eruptions. Its slopes are steep because its lava is relatively viscous, flowing slowly and piling up near the vent rather than spreading out. Over time, this creates a tall, conical shape, but also traps gas. That trapped gas is the key to Sarachev's violence. Unlike open vent volcanoes that release pressure constantly, Sarachev often remains sealed between eruptions. Magma rises, gas accumulates, and pressure builds. When the seal finally breaks, the release is sudden and explosive. This behavior has defined Sarachev Peak throughout recorded history. Eruptions have been documented since at least the 18th century, with major explosive events occurring in 1765, 1878, 1923, 1946, 1976, and most famously in 2009. Each of these eruptions sent ash high into the atmosphere and reshaped parts of the volcano. The 2009 eruption transformed Sarachev Peak into a global icon. In June of that year, the volcano erupted violently, producing a towering ash plume that rose more than 16 kilometers into the sky. The explosion was so powerful that it generated a circular shockwave in the atmosphere, captured in a now-famous photograph taken by astronauts aboard the International Space Station. From orbit, the eruption appeared almost symmetrical. A dark central cone, a bright vertical plume, and a white ring expanding outward across cloud tops. It was one of the clearest visual records ever captured of an explosive volcanic eruption. For scientists, the image was more than dramatic. It was data. The eruption injected ash and sulfur dioxide into the upper atmosphere, affecting air traffic across the North Pacific. Commercial flights were diverted. Ash clouds drifted thousands of kilometers. Satellites tracked the plume as it spread. Despite its intensity, the eruption caused no direct human casualties. There were no towns to evacuate, no infrastructure to destroy. This isolation allowed the eruption to unfold without immediate human tragedy, but it did not reduce its scientific importance. Sarychev Peak demonstrated how powerful volcanic events can occur unnoticed on the ground, yet still influence global systems. Ash from the eruption altered atmospheric chemistry. Sulfur dioxide reflected sunlight, causing localized cooling effects. Fine particles pose risks to aircraft engines. Even remote volcanoes, it became clear, are not isolated from the modern world. The crater of Sarychev Peak is broad and steep-walled, shaped by repeated explosive eruptions. Lava domes have formed and collapsed within it over time. Pyroclastic flows, fast-moving clouds of hot gas and debris, have raced down the slopes during past eruptions, reaching the sea and extending the island's shoreline with new deposits. These deposits are unstable. Waves constantly erode them, reshaping the coast. The island itself is slowly being built and destroyed at the same time. Matua Island bears scars of both geology and history. During World War II, the island was heavily fortified by the Japanese military, which built airstrips, tunnels, and bunkers into the volcanic rock. Many of these structures remain, abandoned and partially buried by ash and vegetation. The volcano has outlasted every human presence here. After the war, Matua was largely abandoned. Today, it is uninhabited except for occasional scientific or military visits. This absence of human activity makes it an ideal natural laboratory for studying volcanic processes without interference. From a geological standpoint, Sarychev Peak is valuable because of its explosivity and relative accessibility for observation, at least remotely. Satellites, seismometers, and atmospheric sensors monitor its activity continuously. Each eruption adds to understanding of how pressure builds, how magma fragments, and how ash disperses. One of the most studied aspects of Sarychev's eruptions is plume dynamics. The symmetry and force of the 2009 eruption allowed scientists to analyze how eruption columns interact with the atmosphere. The expanding shock wave revealed how energy transfers from the ground into the air. This data helps improve eruption models and aviation safety forecasts worldwide. Sarychev also illustrates the difference between hazard and risk. The hazard, the potential for explosive eruption, is extremely high. The risk, the likelihood of harm to people, is low simply because few people are nearby. This distinction is critical in volcanic risk management globally, but that balance can change. If shipping routes shift, if air traffic increases, or if geopolitical interest in the corals grows, Sarychev's eruptions could have more direct consequences. Even now, its ash clouds remain a threat to trans-Pacific flights. Ecologically, life on Matua Island is sparse but resilient. Seabirds nest along cliffs. Grasses and hardy plants colonize ash-covered slopes between eruptions. Each eruption resets succession, bearing existing growth and creating new ground for colonization. This cycle, eruption, destruction, recolonization, has repeated countless times. At night, when Sarychev Peak is quiet, the island feels empty. Waves strike black volcanic beaches. Wind moves freely across bare slopes. The crater emits faint steam. There's no sense of permanence here. When activity increases, that calm shatters instantly. Explosions can begin with little warning. Ash rises rapidly. Darkness can fall in midday. Lightning may crackle within the ash cloud as static electricity builds. These are not rare spectacles for Sarychev. They are part of its identity. The volcano does not erupt often, but when it does, it erupts decisively. It doesn't leak energy gradually. It releases it all at once. This makes Sarychev Peak a reminder of how the Earth stores and releases power on its own schedule. There's no pattern humans can rely on. No countdown, no negotiation. The magma beneath Matua Island continues to rise, stall, cool, and rise again. Pressure builds invisibly. Weeks, years, or decades may pass between eruptions. Then suddenly, the system resets. In an age of constant surveillance, Sarychev Peak still surprises. Its 2009 eruption was not predicted with precision. Its next eruption will likely be no different. Monitoring improves understanding, but certainty remains out of reach. This unpredictability is not failure. It is reality. Volcanoes are complex systems, governed by physics, chemistry, and chance. Sarychev Peak exposes that complexity with rare clarity. It is a volcano that does not need an audience. It does not erupt for effect. It erupts because forces below demand. Release. Seen from space, it looks almost orderly. a plume, a ring, a cone. On the ground, it is chaotic, violent, and loud. Both perspectives are true. In the far reaches of the Pacific, on an island shaped and reshaped by fire, Sarachev Peak stands as one of the clearest examples of explosive volcanism on Earth. A mountain that waits. A mountain that erupts without warning. A mountain powerful enough to announce itself to the planet from orbit. When Sarachev Peak erupts, the Earth is not whispering. It is speaking loudly enough for space to hear. The land that time tore open. In the heart of the American Great Plains, where grasslands stretch outward in quiet continuity, the land suddenly breaks apart. The earth rises into jagged ridges, collapses into steep ravines, and exposes layers of color stacked like pages of an open book. There are no trees to soften the view, no smooth slopes to guide the eye gently downward. Everything here is sharp, fractured, and exposed. This is Badlands National Park, a landscape shaped not by a single event, but by relentless erosion revealing tens of millions of years of Earth's history at the surface. The Badlands National Park lies in southwestern South Dakota, bordering the northern edge of the White River. From a distance, the Badlands appear almost barren, hostile, and chaotic. Up close, they reveal precise structure, bands of sediment, fossil-rich layers, and sculpted forms created by water, wind, and time working in opposition to solidity. The name Badlands reflects early human reactions to the terrain rather than its true nature. French trappers called it les mauvaises terres à traverser, bad lands to travel through. Lakota people referred to it as Makoshika, meaning land bad. These names were practical descriptions. The land was difficult to cross, offered little water, and resisted settlement. Geologically, however, the Badlands are not bad land at all. They are exceptionally informative land. The story of the Badlands begins far from where they stand today. Between roughly 75 and 28 million years ago, this region lay beneath shallow inland seas, river floodplains, and subtropical forests. Sediments accumulated slowly, mud, sand, volcanic ash, layering over time as environments shifted. Rivers changed course, seas advanced and retreated, forests grew, died, and were buried. Each transition left behind a layer. These layers hardened into sedimentary rock, shale, claystone, sandstone, and volcanic ash beds. Unlike hard granite or basalt, these materials are soft and poorly cemented. They resist erosion only weakly. That weakness is the key to the Badlands formation. As the Rocky Mountains rose to the west, regional uplift changed drainage patterns. Rivers cut downward. Rainfall, though relatively low, concentrated along fractures and slopes. Freeze-thaw cycles expanded cracks. Wind removed loosened sediment. Instead of smoothing the land, erosion sharpened it. Soft layers eroded faster than slightly harder ones, creating steep faces and flat ledges. Gullies deepened rapidly. Slopes collapsed repeatedly. The result was a maze of ridges, pinnacles, spires, and ravines. Forms that look violent but are created slowly. The Badlands erode at one of the fastest natural rates in North America, up to an inch per year in some places. This means the landscape is constantly changing, even within a human lifetime. But erosion here does not erase history. It reveals it. Each exposed layer tells a story of ancient environments. Gray bands mark marine sediments laid down beneath the ancient seas. Yellow and tan layers record river floodplains. White bands of volcanic ash trace eruptions hundreds of kilometers away, settling softly across the land millions of years ago. The Badlands are a vertical timeline. This timeline is especially important because of what it contains. Fossils. Badlands National Park preserves one of the richest fossil beds from the late Eocene and Oligocene epochs, roughly 34 to 23 million years ago. During this time, the region supported lush ecosystems filled with mammals that no longer exist. Fossils of ancient horses, three-toed camels, saber-toothed cats, early rhinos, and massive pig-like animals called entelodonts have all been found here. Turtles, birds, rodents, and reptiles are preserved in abundance. These fossils are not scattered randomly. They occur in specific layers, allowing scientists to reconstruct entire ecosystems and track evolutionary change over time. The Badlands are often described as a natural museum, except the exhibits are constantly being rearranged by erosion. As rain removes sediment, new fossils are exposed. Others are destroyed. This makes the Badlands both invaluable and fragile. Preservation requires careful monitoring and protection. The fossil record here helps scientists understand how mammals diversified after the extinction of the dinosaurs. It shows how climate change reshaped ecosystems long before humans appeared. The land itself reflects that change. Millions of years ago, the climate was warmer and wetter. Over time, it cooled and dried. Forests gave way to grasslands. Rivers shrank. Species adapted or disappeared. The Badlands remember all of it. Despite their barren appearance, the Badlands are not lifeless. Grasses, wildflowers, and hardy shrubs grow wherever soil can collect. Bison roam the grasslands above the formations. Bighorn sheep navigate steep slopes. Prairie dogs build colonies across flatter, higher ground. Coyotes, foxes, and birds of prey move quietly through the landscape. Life here is adapted to extremes: heat, wind, drought, and exposure. Human history in the Badlands is layered atop geological history. Indigenous peoples, including the Lakota, have lived in and around this region for thousands of years. The Badlands served as a place of refuge during times of conflict. Its difficult terrain provided protection. Sacred sites and stories are tied to specific formations. In the late 19th century, European American settlers and explorers entered the area, drawn by land, resources, and curiosity. Early fossil hunters removed specimens with little regulation, shipping them to museums across the world. Over time, recognition grew that the Badlands needed protection, not just for their beauty, but for their scientific value. In 1939, the area was designated a national monument. In 1978, it became Badlands National Park. The park also contains land once used as a military bombing range during World War II. Unexploded ordnance remains in restricted areas, a reminder that even this ancient landscape bears marks of modern history. Visually, the Badlands shift constantly with light. At sunrise, shadows stretch across ridges, emphasizing texture and depth. At midday, colors flatten under harsh sun. Grays, tans, and whites dominate. At sunset, the land glows red, orange, and purple as iron-rich layers catch warm light. After rain, the land changes again. Colors darken, mud clings to slopes, the smell of wet clay fills the air. New channels appear where water rushes through. Sound behaves differently here. Wind moves freely, unbroken by trees. Thunder echoes across open space. Silence feels expansive rather than empty. At night, the Badlands become a different world entirely. With minimal light pollution, stars fill the sky. The Milky Way stretches clearly overhead. The land below disappears into shadow, its sharp forms softened by darkness. The Badlands challenge the idea that beauty must be gentle. Their power comes from exposure. Nothing hidden, nothing softened. Every layer is visible, every weakness exploited. They also challenge the idea of permanence. This landscape is temporary. Erosion will continue, ridges will collapse, fossils will be exposed, then destroyed. Over millions of years, the Badlands will flatten into something unrecognizable. What exists now is a moment, one defined by imbalance between rock and erosion. Climate change adds uncertainty to this balance. Altered rainfall patterns could accelerate erosion or change vegetation cover. Increased storms may expose fossils faster than they can be protected. The land responds quickly to change. Badlands National Park is not a monument to stability. It is a record of transition. It shows how landscapes can be shaped not by sudden catastrophe, but by consistent vulnerability. Soft rock, lifted into the open, has no defense against time. And yet, from that vulnerability comes knowledge. The Badlands reveal Earth's history with uncommon clarity. They show how environments shift, how species adapt or vanish, how climate reshapes land long before humans appear. Standing among the ridges, it becomes clear that destruction and revelation are often the same process. The land must be worn down to be understood. In South Dakota, beneath open sky and endless wind, the Badlands remain exposed, unfinished, unstable, and honest. A place where time did not bury the past. It tore it open instead. The mountain built for immortality. High in the rugged mountains of southeastern Turkey, where winter snow lingers well into spring and wind sweeps across barren ridges, there's a summit unlike any other on Earth. Enormous stone heads lie scattered across terraces, their faces calm, damaged, and staring toward the horizon. Bodies once attached to them are gone, buried or destroyed by time. At the very top of the mountain, a massive mound of crushed stone rises like a man-made peak, dominating the skyline. This is Mount Nemrut, a place where human ambition, religion, politics, and geology intersect in one of the most deliberate and haunting monuments ever constructed. The Mount Nemrut rises to an elevation of about 2,134 meters above sea level in the Taurus mountain range, near the modern city of Adyaman. Unlike most famous mountains, Nemrut is not revered for its natural form alone. Its importance comes from what was placed upon it, an enormous royal sanctuary built in the 1st century BCE by one man determined to outlast death. That man was King Antiochus IV of Commagene. The kingdom of Commagene was a small but strategically important realm situated between powerful empires, Rome to the west and Parthia to the east. Antiochus ruled from around 70 to 36 BCE, governing a land caught between cultures, religions, and political forces. Rather than choosing one identity, he attempted to merge them all. Mount Nemrut was the centerpiece of that vision. Antiochus ordered the construction of a vast funerary complex at the mountain's summit, intended to serve as his eternal resting place and a monument to his divine status. At the center of the site is a tumulus, an artificial mound approximately 50 meters high and 150 meters across, built from millions of fist-sized limestone fragments. Beneath this tumulus, Antiochus intended to be buried. To this day, no one has found his tomb. The mound was engineered deliberately to prevent intrusion. The loose stones shift under pressure, making excavation extremely difficult and dangerous. Even modern archaeological attempts have failed to penetrate the core. Whether Antiochus's body lies intact beneath the stones or was lost long ago remains one of archaeology's enduring mysteries. Surrounding the tumulus are terraces carved into the mountain: the East Terrace, the West Terrace, and the North Terrace. Each served a ceremonial purpose, aligned carefully with the sun, stars, and landscape. On the East and West terraces once sat colossal seated statues, each about 8 to 9 meters tall when intact. They depicted a syncretic pantheon, gods blended from Greek, Persian, and Armenian traditions. Zeus was merged with Ahura Mazda, Apollo combined with Mithras, Hercules fused with Varathagna. Alongside them sat Antiochus himself, portrayed not as a servant of the gods, but as their equal. This was no subtle claim. Antiochus declared himself divine. In inscriptions carved directly into stone, he described his ancestry as sacred, tracing his lineage to both Persian kings and Alexander the Great. He established a new religious cult centered on himself, commanding that rituals be performed at Nemrut on specific dates tied to his birth and coronation. Priests were instructed to conduct ceremonies, offerings were to be made, music was to be played, the mountain was to become a permanent stage for eternal worship. The statues were arranged deliberately. They faced outward, gazing across the land Antiochus ruled. Behind them stood massive stone thrones, now fragmented. Before them lay altars for sacrifice. The entire complex was designed to be seen not from a distance, but from within, an enclosed sacred space above the world. Time, however, had other plans. Sometime after Antiochus's death, the kingdom of Commagene fell under Roman control. The cult dissolved. Rituals ceased. The mountain was abandoned to weather, earthquakes, and neglect. Over centuries, seismic activity shattered the statues. Heads toppled forward, separating cleanly from their bodies. Stone cracked. Relief carvings eroded. Snow, ice, and wind worked relentlessly against the site. Today, the most famous images of Mount Nemrut are not of intact statues, but of those massive heads, some weighing several tons, resting on the ground, their expressions worn but still commanding. The faces are remarkably calm. Eyes stare forward. Lips remain closed. Beards curl in stylized patterns. Despite damage, there's no sense of panic or fear carved into the stone. These were not meant to depict suffering. They were meant to depict eternity. The placement of the terraces adds another layer of meaning. The East Terrace aligns with sunrise. At dawn, light spills across the heads, illuminating them gradually. The West Terrace aligns with sunset, where fading light casts long shadows across broken stone. These alignments were not accidental. Antiochus intended the sun to participate in the ritual, marking time and reinforcing cosmic order. Astronomy played a key role at Nemrut. Reliefs depict a lion adorned with stars, often interpreted as one of the earliest known horoscopes. The positions correspond to celestial alignments that may mark the date of Antiochus's coronation. The mountain was not just a tomb, it was a cosmic marker, tying king, gods, and universe together. Geologically, Mount Nemrut is a harsh environment for such a structure. The mountain experiences extreme temperature swings. Winters bring heavy snow and ice. Summers are dry and windy. Freeze-thaw cycles fracture stone. Earthquakes common in Anatolia repeatedly shook the site. That the complex still exists at all is remarkable. Modern awareness of Mount Nemrut came relatively late. In 1881, a German engineer named Karl Sester noticed the ruins while surveying routes for the Ottoman Empire. Subsequent expeditions confirmed the site's significance, but excavation was slow and difficult due to altitude and weather. In 1987, Mount Nemrut was designated a UNESCO World Heritage Site, recognized for its unique combination of monumental art, political ideology, and landscape. Unlike many ancient monuments, Nemrut wasn't built to serve a city or population. It was built for one purpose: remembrance. Antiochus wanted to control how he would be remembered. He wanted his name, face, and divine claim preserved forever, untouched by successors or rivals. By placing his monument on a remote mountain summit, he sought isolation from political upheaval and human interference. In many ways, he succeeded. No city grew around Nemrut. No later rulers repurposed the site. It was forgotten rather than destroyed, and in that forgetting, it survived. Standing on Mount Nemrut today is an unusual experience. There's no sense of bustling antiquity, no reconstructed halls or crowds moving through space. Instead, there's silence. Wind moves through broken stone. Clouds pass quickly. The landscape feels vast and exposed. The statues do not dominate the mountain. They submit to it. This submission changes how the site is perceived. What began as a declaration of power now feels contemplative, even fragile. The king who claimed divinity is reduced to fragments, while the mountain remains. Yet the intent is still legible. Every inscription, alignment, and carving speaks of a man unwilling to accept mortality. Nemrut is not a temple to gods alone. It is a monument to ego, belief, and the human desire to be permanent. At sunrise, when light touches the stone faces and shadows retreat, it is easy to understand why this place continues to draw attention. The scene feels deliberate, almost staged, despite its ruin. At sunset, when light fades and cold returns, the illusion breaks. The statues become silhouettes. The mountain reasserts itself. Mount Nemrut does not glorify conquest. It does not celebrate victory. It does not tell stories of empire. Instead, it reveals something quieter and more personal, the lengths to which a single human being will go to resist oblivion. Antiochus failed to achieve immortality in the way he imagined. His cult vanished. His kingdom dissolved. His tomb remains hidden or lost, but his mountain endures. And in that endurance, his ambition still speaks. In southeastern Turkey, above plains and rivers, surrounded by silence and sky, Mount Nemrut stands as one of the clearest examples of how human belief can reshape a landscape, and how time eventually reshapes belief in return. A mountain built to defy death, a monument claimed by weather, a reminder that even the boldest attempts at eternity must answer to time. The valley where stone took shape. In the high desert of southeastern Utah, far from highways, cities, and forests, there's a valley filled with thousands of strange stone figures. They stand shoulder to shoulder across the basin floor, short, rounded, and uneven, some no taller than a person, others rising several meters high. Their shapes suggest bodies, heads, and silhouettes, as if the ground itself attempted to imitate life, and stopped halfway through the process. This is Goblin Valley, a landscape where erosion did not carve grand cliffs or towering spires, but instead produced an army of compact stone forms unlike anywhere else on Earth. The Goblin Valley lies on the eastern edge of Utah's San Rafael Desert, within the Colorado Plateau region. At first glance, the valley appears chaotic and playful, but beneath its unusual appearance lies a long, precise geological story, shaped by ancient seas, hardened sediment, and millions of years of exposure. Goblin Valley did not form quickly. and it did not form gently. The story begins around 170 million years ago, during the Middle Jurassic period. At that time, this region was part of a vast low-lying basin, influenced by shifting shorelines, tidal flats, and desert environments. Layers of mud, sand, and silt accumulated slowly, settling into thick deposits that would eventually harden into rock. One of these layers is key to Goblin Valley's existence, the Entrada Sandstone. The Entrada Sandstone formed as fine-grained sediment was laid down in coastal dunes and tidal environments. Over time, pressure and mineral cement transformed these sediments into rock, but the cementation was uneven. Some portions hardened strongly, while others remained weak and crumbly. This inconsistency would later determine everything. As tectonic forces lifted the Colorado Plateau, the once buried Entrada Sandstone was raised thousands of meters above sea level. This uplift did not involve intense folding or crushing. Instead, the land rose largely intact, exposing flat-lying sedimentary layers to erosion. Once exposed, erosion began its work. Rainfall in this region is limited but intense. When storms arrive, water rushes across the surface in sudden bursts, exploiting cracks and weaknesses in the rock. Wind scours exposed surfaces, removing loose grains. Freeze-thaw cycles widen fractures as water expands into ice. In most places, erosion produces cliffs, mesas, or arches. In Goblin Valley, something different happened. The Entrada Sandstone here contains a harder cap layer overlying softer material. As erosion removed surrounding rock, isolated blocks were left behind. The softer stone beneath eroded faster than the harder cap, undercutting it and leaving rounded columns topped with bulbous crowns. These are hoodoos, but not the tall, thin spires seen in Bryce Canyon. Goblin Valley hoodoos are squat, wide, and closely packed. Their shapes are dictated by subtle variations in rock strength rather than dramatic vertical joints. The result is density. Thousands of hoodoos fill the valley floor, packed so closely that from above they appear almost organic, like coral or clustered fungi. There are few clear paths. Movement requires weaving between stone forms, each slightly different from the next. Their appearance gave the valley its name. Early explorers and visitors described the formations as goblins, playful, grotesque figures frozen in stone. The name stuck, though there's no folklore associated with it. The resemblance is accidental but persistent. What makes Goblin Valley unique is not just the shape of the hoodoos, but how evenly they occupy the basin. There are no dominant formations. No single pinnacle draws attention. Instead, the landscape overwhelms through repetition. This uniformity creates disorientation. Without tall landmarks, it is easy to lose sense of direction. The valley floor dips and rises subtly. Formations block sightlines. Sound behaves oddly, absorbed by stone rather than echoed. Distance becomes difficult to judge. The effect is immersive rather than monumental. Geologically, Goblin Valley is an example of differential erosion taken to an extreme. Small differences in cementation, grain size, and moisture content determined which blocks survived and which were removed. Over millions of years, these small differences became visible at human scale. Erosion here is ongoing. Each year, small amounts of rock flake away. Hoodoos collapse when capstones lose support. New forms emerge as surrounding material erodes. The valley is temporary, even if it appears timeless. Eventually, the hoodoos will fall. Eventually, the valley will flatten. But that process will take millions of years. The environment around Goblin Valley is harsh. Summers are hot and dry. Winters can be cold, with occasional snow. Vegetation is sparse, limited to hardy desert plants, grasses, shrubs, and occasional juniper or pinyon pine on higher ground. Despite appearances, life persists. Small mammals shelter in crevices. Reptiles use stone surfaces to regulate temperature. Insects occupy microhabitats where moisture lingers. Birds pass overhead, nesting in surrounding cliffs rather than among the hoodoos themselves. Human history in Goblin Valley is relatively recent. Indigenous peoples moved through the broader region for thousands of years, but there is little evidence of permanent settlement within the valley itself. The lack of water and shelter made long-term habitation impractical. Modern awareness of Goblin Valley came in the early 20th century. In the late 1920s, Arthur Chaffin, a prospector searching for oil, stumbled upon the valley. He reported the strange formations, but their significance was slow to register. For decades, Goblin Valley remained obscure. In the 1950s and 1960s, geologists and photographers began documenting the area. Its uniqueness became more widely recognized. In 1964, Goblin Valley was designated a Utah state park, protecting it from development and mining. Unlike many protected landscapes, Goblin Valley allows free movement through the formations. There are no strict trails through the main valley. Visitors are encouraged to explore carefully, moving among the hoodoos rather than viewing them from a distance. This access creates a rare intimacy with geology. You are not standing below cliffs. You are not gazing upward at towers. You are walking among forms shaped by erosion, close enough to touch. This closeness also brings responsibility. The rock is fragile. Climbing or standing on hoodoos can accelerate damage. Some formations have collapsed due to human impact. Preservation depends on restraint. Light transforms Goblin Valley dramatically. At sunrise, long shadows stretch across the valley floor, emphasizing texture. At midday, forms flatten under harsh light, their shapes blending into a sea of tan and brown. At sunset, the valley glows orange and red, shadows returning with depth. After rain, colors deepen. The rock darkens. The scent of wet stone fills the air. New erosion scars appear, small but cumulative. At night, Goblin Valley becomes silent and vast. With minimal light pollution, stars dominate the sky. The Milky Way arches overhead. Hoodoos become silhouettes, merging into darkness. In this setting, the valley feels less playful and more ancient. Goblin Valley challenges common ideas of desert beauty. It lacks grandeur in the traditional sense. There are no towering peaks, no sweeping vistas. Its power lies in scale and repetition. It also challenges assumptions about erosion. Erosion is often imagined as a force that smooths and simplifies. Here, it did the opposite. It multiplied complexity. It created individuality from uniform material. Each hoodoo is the result of chance amplified over time. A slightly harder patch, a small crack, a protected edge. Over millions of years, these differences became form. Goblin Valley is not a ruin of something larger. It is not the remains of collapsed structures. It is the residue of removal, the shapes left behind after everything else was taken away. This makes the valley a study in absence as much as presence. What you see exists because surrounding material does not. The land did not build upward here. It was carved downward. In the San Rafael Desert, where heat, wind, and time dominate, Goblin Valley stands as evidence that even subtle geological differences can create landscapes that feel unreal. Not through violence, not through sudden change, but through patient erosion working unevenly across stone. The goblins will not last forever. Their forms will soften, their caps will fall, but for now, they remain. Thousands of silent figures standing together in a valley shaped entirely by time, a place where stone learned to take shape. The desert that melted. In the remote western desert of Egypt, far beyond roads, villages, and permanent water, the sand itself has transformed into glass. Pale yellow fragments lie scattered across the dunes, some smooth and translucent, others rough and pitted, catching the sun like frozen light. These pieces are not man-made. They were not shaped by tools or furnaces. They were born in an instant of extreme heat, in one of the most violent events ever to affect the Sahara. This is the Sahara Glass Field, also known as the Libyan Desert Glass, a place where the desert briefly reached temperatures hotter than the surface of the sun. The Libyan Desert Glass is found within the Great Sand Sea, a vast expanse of dunes stretching across western Egypt into eastern Libya. The glass fragments are scattered over thousands of square kilometers, making this one of the largest natural glass fields on Earth. For most of history, it went unnoticed, hidden among shifting sands in one of the most inaccessible regions of North Africa. What makes this place extraordinary is not only the glass itself, but the mystery of how it formed. Glass requires extreme heat. Ordinary desert temperatures are not nearly enough to melt quartz-rich sand, which requires temperatures above 1,700 degrees Celsius. To achieve that kind of heat, something catastrophic must occur. The Sahara Glass Field is evidence that it did. The glass itself is primarily composed of nearly pure silica, much purer than most natural glasses. Its color ranges from pale yellow to greenish hues, depending on trace elements like iron. Some fragments are crystal clear, others contain bubbles, streaks, and flow patterns that indicate rapid melting and cooling. These features tell a clear story. The sand was liquefied instantly, then cooled just as quickly. The question that puzzled scientists for decades was simple, but unsettling. What could melt an entire desert? Early theories suggested volcanic activity, but there are no volcanoes anywhere near the glass field, nor any volcanic deposits associated with it. Others proposed lightning strikes, but lightning cannot generate enough sustained heat over such a large area. The scale of the glass field ruled out ordinary explanations. The most widely accepted explanation today is a cosmic one. Sometime around 28 million years ago, during the late Eocene epoch, a massive extraterrestrial event occurred over the Sahara. A large meteor, or possibly a comet fragment, entered Earth's atmosphere at tremendous speed. Instead of striking the ground and forming a crater, it likely exploded in the air. This type of event is known as an airburst. When a cosmic body explodes in the atmosphere, it releases immense energy in a fraction of a second. Temperatures spike dramatically. A shock wave races across the surface. Everything beneath is exposed to heat intense enough to melt rock and sand. In the case of the Sahara, that heat fused surface sand into glass. Evidence supporting this theory comes from microscopic analysis. Some glass samples contain high levels of zircon transformed into a mineral called rhyodite, a structure that forms only under extreme pressure, such as that produced by meteor impacts. Others contain traces of nickel and iridium, elements commonly associated with extraterrestrial material. In recent years, researchers have identified shock features consistent with cosmic impact events, strengthening the airburst explanation. What makes the Sahara glass field particularly unusual is the absence of a visible crater. This absence suggests the object disintegrated before impact, releasing its energy across a wide area rather than concentrating it in a single point. The result was a massive thermal flash that melted sand without excavating a deep scar in the earth. The desert, for a brief moment, became a furnace. The glass cooled rapidly, solidifying where it lay. Over millions of years, wind erosion broke larger sheets into fragments. Dunes shifted, burying and re-exposing the glass repeatedly. Today, pieces lie scattered across the sand, sometimes half-buried, sometimes resting openly on dune surfaces. Despite its age, the glass remains remarkably well preserved. The arid climate of the Sahara prevents chemical weathering. With little rainfall, the glass does not dissolve or degrade easily. Instead, it slowly abrades, becoming smoother over time. Long before modern science arrived, humans encountered this glass. Archaeological evidence suggests prehistoric people collected Libyan desert glass tens of thousands of years ago. Some pieces were shaped into tools, blades, and ornaments. The glass was sharp, durable, and unlike anything else in the region. One of the most famous uses of Sahara glass appears in ancient Egypt. A scarab carved from Libyan desert glass was found embedded in the pectoral jewelry of Tutankhamun, dating to the 14th century BCE. This means the glass was not only known, but valued and transported across long distances. To the ancient Egyptians, the origin of the glass was likely mysterious. Its clarity and color may have seemed divine. It was a material born from fire, in a land already associated with gods, death, and eternity. The Great Sand Sea itself is a dynamic environment. Dunes migrate slowly under persistent winds. Entire areas are buried, then uncovered centuries later. This movement means the glass field is never static. New fragments appear as others disappear beneath the sand. Despite its vast size, the region remains one of the least visited places on Earth. Reaching the glass field requires long desert expeditions with precise navigation and careful planning. There's no infrastructure, no signage, no protection from the elements. This isolation has preserved the field, but it also leaves it vulnerable. In recent decades, collectors and tourists have removed significant quantities of glass, reducing concentrations in some areas. Because the glass is not replenished, every fragment taken is lost permanently. Conservation efforts are complicated by remoteness and jurisdictional challenges. The desert does not announce its boundaries, and enforcement is difficult. Scientifically, the Sahara glass field offers a rare opportunity to study large-scale impact-related melting without a crater. It provides insight into how Earth responds to cosmic threats and what similar events might look like today. The Tunguska event of 1908, which flattened forests in Siberia without leaving a crater, is often cited as a modern comparison. Had Tunguska occurred over a sandy desert instead of forest, it might have produced a similar glass field. This possibility underscores the significance of the Sahara glass. It is not just a relic of the past, it is a warning written in silica. Such events are rare, but not impossible. Earth moves through a cosmic environment filled with debris. Most burns harmlessly in the atmosphere. Some, does not. The Sahara glass field is the silent evidence of one such encounter. Standing among the fragments today, the desert feels quiet, unchanged, eternal. Wind moves across dunes. Heat radiates upward. There is no sign of catastrophe. Only glass, scattered like memory. But each piece carries the same message. At some moment in deep time, the sky delivered enough energy to melt the Earth's surface. Not gradually, not gently, instantly. The Sahara glass field reminds us that even the most stable landscapes can be transformed in seconds. That forces beyond Earth shape its history, as much as those within it. In the western desert of Egypt, beneath the endless sky and shifting sand, the ground once turned to liquid, and when it cooled, it remembered. The glass still lies there, quiet, luminous, and unchanged, waiting beneath the dunes, marking the place where the desert briefly caught fire from the sky. As this journey comes to an end, these places remain, marked by fire, erosion, belief, and deep time. They remind us that the Earth's most powerful stories are written slowly, and sometimes all at once. Thank you for watching Unearthed Secrets. Until next time, keep looking closer beneath the surface of our world.